All right, so the recorder is on. I am going to get started. First thing I'll do today is to go over the homework assignment that was due a few seconds ago. And then we'll talk about the new homework assignment, and then we'll get back on track to talk about pre and post conditions. So that's kind of the roadmap of what we'll be doing today. And as a reminder, there's no class next Monday. Okay, so next Monday, the entire college will be closed, so there won't be any classes. All right, so let me turn on the mic here. Okay, that works. All right, so this is the homework that was due a few seconds ago. Well, maybe by now, maybe a minute or so. So let's go ahead and do this one first. I typically just save the file first without opening it. And once the file is saved, I go to LibreOffice and open it from within LibreOffice. That's the usual way that I do things. Not sure whether if you change the workflow, it will impact, how it is recording your changes, but I don't think that is the case. So this is trace one. When I do the homework or when I work on the traces, I would use one window to display the algorithm. I use new window to display the actual trace. So this way I can have both, basically enabled side by side. And it's a lot easier to do it this way compared to having to flip-flop between the algorithm and the trace. All right, so we are working on sheet one, which is the first algorithm. This is a conditional statement, but it has no else branch. Okay, that's the key. Is it has no else branch.
That's sheet 5.
Okay. Sorry, sheet one. There we go. All right, so with this one, you have to record your trace in sheet 2, which means you have to, start up with the comments, line number, and also one variable per column. In this case, there's only X. The first line number is always pre because you have to state what is the precondition of the entire algorithm. In this case, since I didn't tell you ahead of time what you can assume, you just basically say you don't know what is the initial value of X. Then you move on to line 1. After line 1 executes, X has a value of 4. Then you move on to line 2. From line 1 to line 2, it is just because they are sequential. There's no particular reason, otherwise, why you're going to line 2 after line 1. Okay? There's no control flow in this case. But on line 2, what you need to do is to indicate the condition itself, which is X is greater than or equal to 1. And then you have to indicate whether it is true or not. X has a value of 4, which is greater than or equal to 1. So the answer to that question, yes, is true. It is true that X is greater than or equal to 1. Because of the condition being true, we get into the body of the loop, which is on line 3. So that's why you have to indicate in your trace, you have to indicate the execution of line 2, because line 2, the execution of line 2 is the reason why we get to line 3. Okay, are there any questions at this point? If there are no questions, we get to line 3. And for a few iterations, there won't be anything surprising. X has a value of 4 right now. 4 divided by 2 is 2. And we store that back into X. And then where do we go? Line 2, because we don't track line 4. So back to line 2, X is greater than or equal to 1 is still true because X has a value of 2. So we go back into the body of the loop, which is line 3. We divide 2 by 2, which is 1. We store the 1 back into X. We go back to line 2. X is greater than or equal to 1 is true because 1 is greater than or equal to itself. We go to line 3. And this is where some people would probably lose some minor point values, because in my notes, it was clearly stated that in an integer division, you only keep the quotient. Okay, the quotient of 1 divided by 2 is 0. Okay, but it's not going to be like a majority of the points, so don't worry. I'm not going to knock off the entire question. It will just be a minor point for this particular trace. So overall speaking, it's not going to impact your grade a whole lot, but I do want to make sure that people understand why it is a 0. And then somebody's going to say, yeah, Tag, why are you so picky? Well, that's because in cisp300, this is the behavior in C and C++. You can argue and say that I'm picky. Are you going to tell the C++ compiler that it is too picky? You can, but it's not going to do any good. So that is why I am picky. I'm equally picky for the same reason in this class, because I want you guys to be ready for cisp360. Okay? So it is a 0 here. You go back to line 2. You cannot get out just yet, because I know most of you know, oh, x now has a value of 0. It's time to get out. But you cannot get out until you get back onto line 2, identify that x is greater than or equal to 1 is false. Then you get out, which means you get to post. Are there any questions about this trace? Questions? All right. Okay, so what I will be grading on is, part of it is dependent on whether you follow the steps or not, okay, whether you indicate the execution of line 2 and then line 3. Particularly this transition, getting out of this entire algorithm from line 2, this is important, okay? That is important to me, because if you skip from line 3 all the way to post, you're skipping the reason why you're getting out of the loop, okay, which is important. This one is sort of important, but it's not nearly as important. I would take out maybe 1 point out of, I don't know, 3 or 4, just out of this particular question, okay? But you have 2 more traces, so it's not going to be a major impact on your grade. All right, so this is done. Let's move on to sheet 3. This one is a little bit tricky, because if you try to read this as a person, you basically go like, oh, there's nothing to do. I can just go to post right away. But that's not true, because when you have a trace like this, you have to do exactly what the code is telling you to do. Okay, so that's one thing that you will learn in this class. In your other programming classes, sometimes you don't want to look at things and understand it as a person. You want to look at it from the perspective of the computer, and what will the computer actually do. So let's go ahead and trace this one. We need comments again, because we have a condition on line 4. We have line number, and we have a single variable y in this case. The precondition is, since I didn't tell you anything ahead of time, you have to assume that y has an unknown value to begin with. After line 1, y ends up with a value of 20, because that's the assignment statement. The next line to track is not line 2, okay, because I said it quite a few times already. We go straight to line 3, because line 2 doesn't do a single thing. It is only there to mark the beginning of the post checking loop, but it doesn't specify any operation. So on line 3, we are multiplying y by 2, so 20 times 2 is 40. We store 40 back into y. So y now has a value of 40. Then we go to line 4. On line 4, we perform the comparison, which is y is greater than or equal to 10, and then we have to indicate it is true. Now, it was true already before we perform the operation of line 3, but you don't have a choice. You cannot skip it, because this is a post-checking loop, which means you check the condition after you perform at least one iteration. So you don't get a choice. You have to perform line 3 first, and that's why y ends up with a value of 40, which is also greater than 10. Okay, but that's the reason why we're getting out of the loop. And get the post, and we're all done. Okay? So with this particular one, the key concept is that we have to get to line 3. Even though it looks like we don't have to go to line 3, we do. Because that's what the trail map tells you. Okay, the trail map, remember, it doesn't give you a choice until after the operation, until line 3. Then you have a choice to whether to go back or not. Yes?
Why do we have to put 3 when we already know the value of y is 20 to tell us?
Because the computer does not. Well, it knows the value is 20, but it doesn't know the significance of having a value of 20. The computer cannot look ahead of time and look at line 4 and go like, oh, since I have to get out anyway, might as well get out now. It doesn't operate like that. It has to go through, remember the trail map? It has to go through the trail map. So when we do things in this class, we are doing it the same way as what the computer would have done. Is that okay?
Yes.
Okay. So that's why the solution to this particular question is the way it is here. And then we move on to sheet 5 as the algorithm. This is the only one where I give you initial value, so you don't need to specify pre anymore because I have already done that. Okay, so that's the precondition. Line 1 is going to add the x and w. X has a value of 60, w has a value of 20. So total is 80. We use the value to overwrite x, so x ends up with a value of 80 here. We go to line 2 because they are sequential. So line 2, you need to write down something in the comments because you have to tell me whether x is greater than or equal to y is true or not. Okay, so let's check. X has a value of 80, y has a value of 65, 80 is greater than or equal to 65, so the answer is true. Because the condition of the conditional statement is true, you have no choice but to go to the then branch. Okay, there's no else branch here. Okay, that one just skips all the way to the end. But we do have to go through the then branch in this case, which is the true branch, which is starting on line 3. On line 3, we are subtracting the value of y from x. Y is 65, x is 80. 80 minus 65 is, now for those of you who know how to work a spreadsheet and you don't want to do your own actual calculation, this is what you can do. You can type an equal symbol to specify this is a formula, and then you specify, oh, it's whatever in this cell minus whatever is in that cell, press the enter key, and let the spreadsheet do the calculation for you. Okay, so you don't have to do it this way. Okay, this is not a spreadsheet class, but since we do have a spreadsheet and I can do this, that's why I'm doing it. I don't trust myself with arithmetics. Okay, I mean, why not? I mean, there's the question. Why not? All right. So after line 3, we proceed to line 4. So here is line 4. Line 4 just wants to add 1 to the current value of z. So if you want to carry on the same thing as last time, you can press the equal symbol here, and then click on the cell that you're supposed to update, and then say +1, press the enter key. Now we have 8. Okay. Now this one I'm fairly sure that I can figure out 7 + 1 is 8. But doesn't hurt to show you, how to use a spreadsheet, because that's the whole idea of a spreadsheet. It is a gigantic calculator. Okay, for each cell you can specify a formula that is based on the values of other cells. Okay, and it can be very useful. Okay, even in your other classes, this can be very useful. Think about your physics classes, where you have to go through all the calculations and whatnot. Well, if you can figure out the relationship between the cells, you can just specify the formula and let the computer do all the actual calculations. All right, after line 4, there's nothing else to do because this is the end of the then branch. After the end of either branch, you go out of the conditional statement. But there's nothing after the conditional statement, and that's why we get to post right away. Are there any questions about this trace? Yes?
So if we went back to number 2 again, just to say true, that would be wrong.
You do not go back. This is a conditional statement. It does not move back. Because the trail map of a conditional statement is like this, right? You have 2 branches. You have something to do here. You might have something to do here. Maybe not. Doesn't really matter. But the 2 branches will still merge back into one, and you get out. There's no trail back to the beginning.
Okay. So we'll get marked off.
Oh yes, definitely. Because that's not how the computer would have done it. Okay? And that's kind of a conceptual thing, so you really have to kind of make sure that you remember a conditional statement is not a loop. It does not go back at all. Now, if a conditional statement is inside the loop, yes, then you have a way to go back, but it's not because of the conditional statement. It is because the conditional statement is inside the loop.
Say that again?
You have a conditional statement that is inside the loop. Okay, I'm getting better at this. So if your conditional statement is here, it is inside the loop, so that means, yes, it does go back to the beginning, but it's not because of the conditional statement itself. it's because of the loop structure, which is outside of the conditional statement. Yep. Yeah.
If it did have an else branch
Yeah.
for your trace, do we need to comment on the else branch? Or
No,
not?
because you can only take one branch or the other. So if the condition is true, you have to go to the left-hand side. Then your trace will only reflect what happens when you go through the left-hand side. On the other hand, if the condition is false, then you can only go through the right-hand side. Then you can only tell me what happens when you go through the right-hand side. So for each time you get through a conditional statement, you can only go through one side, either the left-hand side or the right-hand side. You cannot go through both at the same time. Yep, go ahead.
So if line 2 was false, would the trace just end right there?
Yes, if line 2 gives you a result that is false, then the next line is going to be post. Because this particular statement has no else, which means the else branch, there is an else branch, there's just nothing to do on the else branch. Yep.
What type of problem was the first sheet? Was it like a pre-check?
Say again.
What type of problem was on the first sheet? Was
On
it
the
a pre-check?
first sheet, it's a pre-check.
Okay.
Yep.
So I'm kind of confused, why did we stop at 4?
And what do you think it has to stop at? Where else? Where do you think it should stop at? I'm not asking you to challenge you, but I'm trying to understand your thinking, so that way I can try to explain why it is.
Okay, I know we should stop at 4, but wouldn't we go back to line 2?
It does not go back because a conditional statement has no way to go back. A conditional statement goes to a certain place where you have two ways to proceed. Okay? You have to choose one way or the other way based on the condition. If the condition is true, you go this way. If the condition is false, you go the other way. Let's say you got something else to do here, you get something else to do here, but the two branches will merge, and then you get out. There's no path back to the beginning. It is not a loop. Okay? Any other questions?
So the first two are pre-checking, and the repeat one are called what?
It's a post-checking.
Okay, that's the post-checking. And the last one is all.
It's a conditional statement. Yep. All right. Are there any questions? So if you're not really familiar with the terms, what is a pre-checking loop, what is a post-checking loop, what is a conditional statement, it might be helpful to read the notes again, because all of those terms will be important for the rest of the entire semester. Okay? These are really just the beginning. Okay? I'm giving you the most basic Lego blocks at this point. So everything else will basically be building upon these things also. But we'll be adding other stuff on top as we go. Okay, any other questions? Okay, no other questions? I see people squinting, so there might be questions. No? All right. Well, go ahead.
No, go.
You good?
Yes.
Okay.
Thank you.
All right, so at this point, we're going to switch gear and talk about pre and post conditions. And the reason why we are doing this is because we want to be able to analyze a program and figure out whether the program is correct or not without tracing it, okay? So this might be confusing because we have been tracing stuff for a while, and your current homework assignment is tracing. Well, I need to show you that too. So your new homework assignment is nested, control structure traces. I'm just going to go ahead and show you what it looks like, and you have to figure out how to do it.
Can you just show us the first one, and then we'll take it from there?
Well, there's only one.
That's a show. That's good.
All right, nested control.ods. So it looks like this. It looks a little bit nasty. For those of you who do not feel comfortable with, just, oh, Lord, I have a mistake here. No. Oh yes, I did make a mistake. Darn it. Okay. this line and this line should be interchanged. So this really should be y gets y plus 1. I'm going to fix it in the homework assignment, so I will re-upload this file to Moodle. So if you have already gotten started with this one, you have to download it again, or do this fix yourself. Okay, there we go. All right, so what you need to do is to figure out what it looks like. Okay, if you do not feel comfortable just looking at the code and know what it does, draw a picture. Okay, when you draw the picture, you can do it from the outside in, you can do it from the inside out. It is your choice. It doesn't matter, okay? But for the sake of drawing, it is easier to draw it from the inside out. In other words, what you do is you go to the deepest part with the most indentation. With the most indentation, that will be from line 5 to line 10, okay? That's the innermost portion of this structure. So you draw a picture representing these lines, okay, which is a conditional statement and a assignment statement outside of the conditional statement. So you draw this first. But what is that stuff in? It's in a pre-checking loop. So draw a pre-checking loop around this block of code. Okay? So the next thing you do is to draw a a pre-checking loop which starts from line 4, ending on line 11, around what you just drew a little bit earlier. Then you have something else that is after the pre-checking loop, which is this one here, and something to do before, which is this one here, okay? So you have to add these two around the pre-checking loop. Then you end up with a bigger block of code. What do you do with that bigger block of code? That whole thing is inside yet another pre-checking loop. So you draw the structure of another pre-checking loop around that big, huge chunk of code. So this way it's easier to do it this way because you don't run out of space as easily. If you do it from the outside in, by the time you get to the innermost portion, you might find out that, oh, I don't have space to write down the instructions anymore. But if you do it from the inside out, and you use your space sparingly, you should be okay. So once you have the picture, then you might want to add arrows because you want to indicate certain paths. Well, all paths are only one way. So you want to indicate you can only go in from here, you can only exit from here, and so on. Then the rest is really just following those directions. Are we doing okay so far with how to get started with this one? Yes.
Can you do an example? Maybe not exactly this one, but the example kind of like this, so we kind of know.
I would say the one in the reading material would be a good one. Not really, but I can show you where it is. Okay, so the reading material, which is called nested statements, if you open this up, we have seen this one already. So I give you something like this, which is nasty, but not as nasty as your homework assignment, okay? And the picture is down here, and the actual trace is down here. So I would go with this one, okay? All right, getting back to the example. I'm gonna get rid of the stuff that I don't need anymore. There we go. So this is your homework assignment. Once again, draw the picture if you do not feel comfortable just reading the text and try to figure out what it's going to do. But remember, eventually, okay, in about 2 weeks of time, I want everybody to feel comfortable tracking down this kind of logic without a picture. Okay? That's kind of the prerequisite of what you need to do when you write programs. Because people who need to refer to a picture all the time, they won't be able to code effectively. Okay? What is effectively versus not effectively? What makes that difference?
They'll still be able to write a code.
They will still be able to write the code. The question is somebody going to hire that person? That really is the bottom line. Okay? I mean, I can dribble. I can shoot a basketball. Can I get into NBA? Is it NBA, the Basketball Association?
If you play good,
They won't even have me to pick up the basketball because I'm too slow even for that. Okay, but I'm able, right? I mean, I can run, I can walk, I can shoot, the ball. It might take me 20 times to get it through the hoop, but I can do it. But can I join the team? Can I be a basketball player and make a living out of playing basketball? Extremely unlikely. It's the same thing with programming. Okay, the question is not whether someone can do it or not. The question is, can someone do it effectively or competitively, so that the employer feels comfortable and go like, oh, I know you are a effective programmer, and so paying you so much money, gets this much work done, is a good deal. Okay, so that's the bottom line. So it's not about whether it can be done; it is about efficiency and effectiveness. This is actually what we talked about the other day. Okay, so I got to remember to do one thing, which is to save the document and re-upload it to Moodle so that you guys have a correct starting point. That's number one. This is the right one. Okay, so I saved the file already. You can tell whether the file has been updated but not saved, because if I make any updates and if I do not save, this little floppy disk is going to be highlighted. It's going to be lit. Okay. One of these days they have to change the icon, because in about 5 years people won't know what is a floppy disk. Yeah, what is that icon? It looks like a little square, but what is it? Well, nobody has floppy disks anymore. Yep.
I've seen some people who've seen floppy disks, like young people who've never actually seen them before. They're like, oh, hey, it's a save button, a physical save button.
Press it. Press it.
The paperweight.
Oh, you know what? That makes a gadget device that people can actually sell. Make a floppy disk thing that is a Bluetooth device. Okay, so, and you have to install, a companion app or program on a PC. So when you press the actual floppy disk looking Bluetooth device, it will trigger whatever app you're using to actually save the file, which is usually just Control-S. Just play the macro of Control-S. I bet you it will sell like hotcakes. Okay, so there you go. If one of you decide to drop the class because in 2 weeks you have just become a multi-millionaire, I can understand. See, I throw these ideas at you, and if you really want to become a billionaire, you have to run with it. But I have no guarantee that you will actually become a billionaire. But you have to do it quick, because remember, this stuff is on YouTube. All right, so now that I have the file saved, I'm going to go back to Moodle and change the assignment, because it is now different. So I have to find out where that stuff is, which is this one, and change, do the edit. Excuse my navigation here, because I know it looks really confusing from your perspective. So click here, delete the file that I already have, re-upload the one that I have changed, which is this one. Check the time, it's okay, upload. And save. There we go. Okay. The reason why I knew it wouldn't work is because I have y initialized to 2 here, but I have x being incremented over here. So if y is already less than x and I keep increasing x, the loop will never exit. That's the reason. And then the same thing over here. X is initialized before the outer loop, and the only reason I can get out of the outer loop is when x is no longer less than 5, but since I'm only incrementing y over here, it will never get out. So that's how I can kind of quickly identify, go like, oh man, I swapped the variables. Okay, but anyway, at some point you guys will be able to pinpoint problems like that really quickly too. So I'm gonna get rid of this one. And because from here on, I don't really need to use spreadsheets anymore, because when we talk about pre and post conditions, it is not about tracing. It is all about mathematically proving something is correct. Okay? Are there any questions at this point before we get into this sort of thing? Okay, no questions? All right. So the first thing we will do is to talk about what is a precondition, what is a post-condition, and what is the notation. How do we specify this is the precondition and that is the post-condition? So instead of reading it out of my notes, which is going to be boring and it's going to be a little hard to track, this is what I'll do. I'm going to use a just plain text editor here as my virtual whiteboard. And I'll just write a single line of code and then talk about the pre and post conditions. Yep, go ahead.
How do you get it to number the lines automatically?
Say again?
Is numbering the lines automatically, is that from mousepad alone, or can you do that in WordPad or what?
It's from this particular app. It's called Mousepad. So when you go to View, you can select and turn on and turn off.
Do that in WordPad or Notepad?
Probably not, but there's Notepad++ that you can download and install. It's a free program you can download and install in Windows. And that one is kind of useful for programming because you can do syntax highlighting. If you're editing HTML documents, it can actually do syntax highlighting for you. If you're programming in C and C++ or any actual programming language, you can turn on syntax highlighting as well. So Notepad++ is the name. In fact, I'll just go ahead and point out here. Notepad++. It's open source. It's free. And let me see if I can. Yeah, there's a screenshot right there. So it has line number on one side, and even analyze the code for you, so you can figure out the open and close curly braces. So you can collect a block, if that's what you want to do. But it only works with actual programming languages. It doesn't work in this class because we're using pseudocode. But when you move on to cisp300, that program will come in handy. It's not big, it doesn't need a lot of space to install. You can install it onto a thumb drive. So that way you can carry the application with you wherever you go. So great little application to download and install. Okay, so back to Mousepad here. So let's say I have line 4. Where's line 1, 2, and 3? I don't know and I don't care, okay? Because the pre and post condition is just about that, okay? Tell me what is the condition immediately prior to the execution of line 4. And then I have a way to figure out what is the post condition immediately after the execution of line 4. That is the whole nature of what is a pre and what is a post condition. So on line 4, we'll start with something relatively simple. Okay, we'll just say that x gets a value of, 7. Okay. All right. So this is what line 4 looks like. I don't even know what is lines 1, lines 1, 2, 3, or 5, 6, 7, and so on. We focus on one single line at a time. And before I forget, because I tend to do that, here's the row sheet. It is a row sheet from Monday, so many of you already have your name on it. Just initial, to the right-hand side of your name already on the sheet. Yes?
What if we tried to add the class and our name isn't on it?
Add your name to the second sheet. Just write down your name and then sign after that. Okay. All right. So the precondition of a line is this notation. Just pre, and then in parentheses, we indicate the line number. So this is basically saying that this is the pre, whatever follows on the right hand, on the other side of the equal symbol, is the precondition of line 4. This is a condition that is guaranteed to be true. Is that okay? So it can be a bunch of stuff, okay? So let's say we have 3 lines already prior to this, and those 3 lines, for whatever reason, I don't know why, okay? For whatever reason, because of those 3 lines, we know that there's a value, there's a variable k, and k is guaranteed to be less than y, and we also know that z equals to 20, okay? This is guaranteed, okay? It has to do with the lines before line 4, okay, lines 1, 2, and 3. And this is what I know at this point. Right before we execute line 4, I know this is true. So now the question is, what is post 4? What is the post condition of line 4? What is it? Yep.
K is less than Y and Z equals 20 and X is 7.
Exactly, okay? Well, because line does, okay, first of all, does line 4 do anything to K, Y, or Z? Nothing, right? So the relationship between K and Y wouldn't be affected by line 4. Is that okay? What about the fact that Z equals to 20? Am I changing Z on line 4? No. So Z equals to 20 would still remain the same, right? Because I didn't do any change, I didn't make any changes to Z. So that means I can keep this, I can keep that. But on top of these two things that I already knew before line 4, one additional thing that I know at this point is X equals to 7. Are we doing okay so far with the rationale behind knowing that one extra piece of information as in the post condition?
Why are you writing pre-parentheses 4 and post-parentheses 4?
Because that's the notation. Pre-paren 4 means the precondition of line 4. Post-paren 4 means the post-condition of line 4. That's just the notation that I use in this class. Yep.
Is there a reason why you're using equal signs instead of arrows now?
Aha. Okay, I was just about to mention that. Why do we have equal here when there's assignment here? Yep.
Query versus assignment.
Exactly. Okay, one is a statement. One is stating and asserting that X does equal to 7. Okay, let me highlight which portion. This is an assertion. In other words, it is telling us that X does equal to 7 as a post condition. The other one is an assignment operation. We are changing X to 7 from whatever it was before. So one is changing it, the other one is stating that this is now true. Yep.
If the precondition of X assigned at 7 was 8 instead of 7, and you were asserting that X is equal to 8, would it make that post line invalid?
Well, we'll take a look at that next, okay? So I want to start with something simple where we did not know anything about X prior to line 4, okay? And then we'll move on to something that's a little bit more complicated, okay? So is this okay so far? Just given this one example.
Even though
So how come on line 1, you put the 4 next to it?
Well, okay, the numbers to the left-hand side, I'll just turn it off because, I don't really need to refer to line numbers in this case. Those are just line numbers of the document itself, and 4:X gets 7 is the line in the pseudocode that I'm concerned about. Okay. Yep.
So in this situation, say if there was like 30 lines or 300 lines, would you be carrying down the post condition of every line all the way down? So, I mean, if you were to write it out on line 500, you would have the post conditions of all the previous lines on that one line?
Well, but they can simplify, and sometimes we lose items. So, the complexity of the pre and post condition depends on the structure of the code. But the idea is the same, okay? We do move on to the next one and then the next one. But I just want to focus on one line at a time at this point. Yep, go ahead. You had a question earlier.
yeah, actually my question was, because you have those lines and then you have the pre-parentheses 4 on line 3, I was just confused.
Oh, okay, yeah, I just took out the line number of the document itself, so that would not interfere with what we're talking about.
So the pre-parentheses 4 is actually now on line 1?
No, that's just a statement. That tells me what I know for sure is true immediately prior to the execution of line 4.
Something the same type of idea that we had on our homework on sheet 6.
No, this has nothing to do with tracing. Okay, this has to do with what do we know for sure is true prior to the execution of the line, but it's not based on tracing. Okay. Are we still doing okay so far at this point? Okay. All right, so let's move on and talk about another example. which is kind of like this one, except it's not the same, okay? So let's say we have line 301. We don't know what happened to the previous 300 lines or the lines after this. It's not important. And the only thing we know is, okay, let's make this a little more fun. So we say that y gets the value of k plus 1, okay? And I have to tell you what is the precondition, okay? So the precondition of this is k does not equal to z, and z is less than w, okay? That's the precondition. And I'll throw in one more thing. I'm going to say y equals to 600, okay? That's the precondition. Don't ask me why that is the precondition, because it has to do with the rest of the program. I just know that for sure, right before line 301 executes, that has to be true. K and z cannot be the same. Z has to be less than w, and y equals to 600 exactly. That's guaranteed, okay? So now the question is, what can I say as the post condition of line 301? First of all, which variable is changed by line 301? The one on the left-hand side, which is y, right? So that means it doesn't change k, it doesn't change z either. So whatever we knew about the relationship just between k and z is maintained, because those two variables do not get affected by this line. Is that okay?
Yes.
So if it doesn't get affected, hey, we can just keep them. K different from z has to be true at this point. What about the relationship between z and w? Did any one of these two variables change because of line 301?
No.
Nope. So if z was less than w before, it will still be less than w at this point. Okay? So we keep that. What about this one? Can I still say that y equals to 600? No. Because we have no idea what it is now, except that it is k plus 1.
Right.
So we have to toss y equals to 600, because that can no longer be guaranteed. Instead, we say, okay, the only thing we know at this point is y does equal to k plus 1 at this point. Well, how does it relate to the rest of the variables? We don't know. Okay? Now this you cannot do using a trace, because with a trace, you need to know the exact value of every variable in order to carry on and go to the next step. With this, oh, look at this. I have no idea exactly what is y anymore. I just know how it relates to k. That's all. But what exactly is k? I don't know either. I just know that k is not the same as z. That's all I know. That is the difference between tracing, which relies on knowing the exact value of every variable at all time, as opposed to using mathematics to deduce what we know after the execution of a particular line. Are we still doing okay so far with this? Okay, all right, very good. So what we'll do next is to introduce something that is, I'm changing the order, okay? The notes, actually doesn't do it in this particular order, but I think this is a little bit better because it really helps to illustrate the concept of all of these things. So this time I'm going to give you a control structure, something that we have seen already. Okay. Have we seen these 5 lines of code? How many times? I lost track. Okay, many, many times. But we know what it does, okay? And I claim that this code is going to find the maximum of x and y and store the maximum in z. Remember, that's my claim. But how do we know it works? Well, we traced it a few times, right? Seemed to work. But when you're tracing, you can only prove that it works for the few instances, only for the test cases. There's no guarantee for the next test case that you throw at the algorithm, which to me is not a comfortable feeling, because I want to know that this works for all cases of x and y. Are we doing okay so far?
Yes.
Okay. So the biggest and kind of easy question in a way is, what should I say about what we know prior to the execution of line 1? Because we cannot make assumptions. We cannot say that x equals to 5, y equals to 60, because that will lock down the rest of the code and say, oh, it only works when x is 10 and y equals to 60. I don't want to lock down anything. So the question really is, what kind of expression is true regardless of the value of all the variables that we have in this code? It's a trick question. Yeah.
X is equal to X, Y is equal to Y.
X equals X, Y equals Y. Yes, that is absolutely true. But what is the easier way to say that? Because you're telling me something that is always true.
X is equal to C and Y is equal to C.
No. Yeah.
Is it X is not equal to Y?
There's no guarantee, because remember, we don't know the value of x and y. I want to prove this algorithm works in all cases, even when x equals to y, and it works for any value of x and it works for any value of y. In other words, I don't want to make any assumptions. Yes?
Is pre-1 just true?
Exactly. The simplest expression that is always true is true itself. Thank you. Does that make sense? Sort of? Or is it too simple to make sense? I mean, it does happen. I mean, there are things that are too simple to make sense. Yes?
So if we make it true, does that kind of make sure it's completely accurate without assumptions, or if it's true, that's it?
It means I don't make any assumptions. Because the statement or the condition true, does that say anything about x? Does true as an expression, as a value, does it say anything about x? No. Does it say anything about y? No. Does it say anything about z? No. It simply says, hey, this is guaranteed to be true, which makes sense. True is guaranteed to be true. Yep, go ahead.
But you're saying it's true so we can follow it.
Yeah. Well, you have to start with something.
Yeah.
Okay. So then we'll go ahead and try to analyze this code and figure out, how do we work out the pre and post conditions of all of these different items here? It might be helpful to have a picture. Okay, so I'm just going to borrow this picture here. X is greater than y is the condition. I always put the true branch to the left-hand side and the false branch to the right-hand side. Here we have a statement which is z gets x, z gets y over here. They merge, okay? Are we okay with this picture? Now we'll go ahead and put some line numbers into the picture. So I'll use the red pen to indicate the line numbers. This is line 1, okay? Line 1 is right at the fork where you can go one way or the other way. Line 2 is right here. This is line 2. This is line 4. And line 5 is kind of down here. Okay, if you want to look at what line 5 is, it's kind of down there. Okay. Are there any questions? What about line 3? Line 3 doesn't do anything. Okay, it is a separator. It separates the then branch from the else branch when we are writing it in a text mode. Okay, so in the analysis of the code, it has no significance when we're trying to analyze the pre and post conditions. Is that okay? And that's why line 3 does not appear anywhere in the picture itself. Are we still doing okay so far? Question?
What would number 3 say if it was like written as opposed to the picture?
Say again?
What would the line 3 say if we had the code written rather than the picture?
Line 3 serves the purpose of a comma. It separates one thing from another thing. Because without else, how are we going to see this code? without line 3, without the else, we'll think that, hey, line 2 and line 4 are both in the then branch. That's not what I want to do. I want to do an else branch. So line 3 doesn't do anything other than separating the then branch from the else branch, but only when we are representing the logic in text. Because otherwise, there's no indication. Where's the end of the then branch and where's the beginning of the else branch? We cannot tell. But when we do it in a picture, well, it's quite obvious which part is the then branch and which part is the else branch. So line 3 has no place in the picture itself because it's no longer needed. Okay. All right. So looking at this picture, we'll try to figure out a few things. We don't want to do post 1 anymore because there are 2 post 1s. Because post 1 can be here, can be over here. So I don't want to refer to post 1 anymore. Instead, I'll write about pre2. So we want to figure out what is pre2 on one side. We want to figure out what is pre4 on the other side. So when you look at the picture, all I'm saying is we know that at this point, so as someone walks through this path, at this point, the only thing we know is true itself. In other words, we don't know anything. Okay? We're here, but I don't know a single thing. That's okay, not a problem. The next question is, what is pre2? This is line 2. So pre2 is asking what condition has to be true right before we execute line 2, which is this branch here. In other words, we are asking, while I'm here, what do we know for sure has to be true? Go ahead.
X is greater than Y is true?
Exactly, because otherwise we wouldn't be here. The reason why we are even here on this particular branch is X is greater than Y is true. So that's why the precondition of line 2 is X is greater than Y. That's all we know for sure. Because otherwise we wouldn't be about to execute line 2. Is that part okay? What about the other one? What about right before we execute line 4? What do we know for sure if we are about to execute line 4? The other side, right? How can I possibly end up over here? What steered me into this direction? It's false. The condition is false. X is greater than Y is false. That's all we know. But we like to express things that are always true. So if we know that X is greater than Y is false, what has to be true? Y is...
Or X is greater or equal to Y.
X is less than or equal to Y. Or it is not the case that X is greater than Y. Either way is okay. So I'll just go ahead and pick one of them, and I'll pick the one that is easier to understand, which is X is less than or equal to Y. Is that okay? Does everybody follow, Y pre2 is X is greater than Y, and pre4 is X is less than or equal to Y? Yep.
Would it be okay if you wrote X, or would it be okay if you wrote Y is greater than or equal to X?
See that?
Would it be okay if you wrote Y is greater than or equal to X and both sequences?
Yes, it would be the same.
Okay.
Yep. Okay, so right now we are going to, okay, I think this is fine. All right, so now that we know this is pre2, what is post2? So we focus on just post2 in this case. In other words, the rest of the code does not matter anymore. We focus on just line 2 because we already know what is pre2. We just need to know what is post2 based on pre2. What do you think? The precondition of line 2 is X is greater than Y. Does line 2 change X or Y? So can we keep the fact that X is greater than Y? Yeah. But what else do we know?
X is equal to Z.
Z and X are the same. Okay, very good. So that's exactly what's going to happen. Okay, so the post condition of line 2 is X is greater than Y and Z equals to X. Is that making any sense? Because we get to keep what we already know about X and Y at this point, but on top of that, because I just copied the value of x into z, we also know that those two must be the same. Is that okay? We can apply the same thing to line 4. So the post condition of line 4 is x is less than or equal to y, because we did not change either of those two. The only thing on top of that is we also know that y and z must be the same, because I just copied the value of y to z on line 4. Is that okay? This is great, okay? We are analyzing the logic of this code, and we have just figured out post 2, which is this point, post 4, which is this point. So if you want to document the whole thing, this is pre-1. This thing here is pre-2. This thing here is pre-4. This thing here is post 2. This is post 4. We are almost done. But here comes the tricky part. These two paths will merge before we get to line 5. So what can we say about post 5? In other words, immediately after this entire conditional statement execute, what can we conclude? Yep, go ahead.
Say x is greater than y and z equals x, or x is less than or equal to y and z is y.
Exactly. So if I want to go step by step, okay, post 5 is merging the two paths. So by the time you're standing here, you don't remember which path you took to get here. So the only thing you can say is this can be true or that can be true, but I don't know which one, because I'm just standing here. I do not remember how I got here. Is that okay? So we'll just say that, so to do it step by step, okay, this is what we can state right away. We can state right away that by the time we get to the end of the conditional statement, at least one of these two has to be true. Now, do not exclude the possibility that both of them can be true. Okay? There's no exclusive or here. We just know that at least one of these two conditions have to be true. Are we doing okay so far with this code, with this analysis? Sort of?
Yes.
Kind of? Okay. All right. So, but we already know what is post 2. I mean, that's something that we figured out earlier. So the way I do this is, since I have an editor, I do something like this. So this way, I don't have to worry about not closing parentheses. Then I just copy and paste, and then we copy and paste. Cool. So now we have the whole thing figured out. In other words, we are guaranteed that by the time we get to the end of this algorithm, after line 5, we are guaranteed that that condition, let me highlight which one we are talking about. We are guaranteed that this condition has to be true. But Tag, what if x is 1 and y is 5? What if x is 100 and y is -5, and so on? It doesn't matter. This has to be true. So now the big question is this expression, the one that I have just highlighted, does it state that z is the maximum? Remember how we expressed, whether z is maximum or not? Okay, so let's see what we can do about this. Okay, now z is the maximum of x and y means, okay, this is something from the previous class, right? So we know that z is greater than or equal to x, z is greater than or equal to y, and it has to be equal to at least one of them. Okay, so we know that z equals x or z equals y. One of these two has to be true. At least one of these two have to be true, because x and y can be the same thing as well. Okay, you look at these two expressions and you ask, well, are they really the same thing? You look at this expression, which is the result of analyzing the pre and post condition stuff. Okay, this is the result of executing this algorithm. You look at the other expression, which is this one here. This is the desirable outcome. This is how we define z is the maximum of x and y. So now the question is, are they specifying exactly the same condition? That is the question. What do you think? Well, I got a warm and fuzzy feeling that they are. That's not good enough. Can we prove that they are exactly the same? Okay, how do we do that? We use, sorry?
Variable substitution.
Variable substitution, what do you mean by that?
If C is equal to Y, that means C and Y can be interchanged in the other condition. And if X, basically you replace the Y variable or whatnot with the Y variable on the post 4 and the X variable on the post 2 with the Z variables.
Okay. I can see your line of reasoning, and it's good, okay? But I want to do this in a much more formal way. I want to do it the math way, the way that mathematicians would do it. Okay? So we'll do it in using what? Algebra. Okay? Remember, in usual regular algebra, you're given one expression, and you have to prove that that expression can also be rewritten as blah blah blah. Remember those things from high school? Okay? Give you one quick example. X plus y squared, okay, your professor may ask you and say, okay, show that this is x squared plus 2xy plus y squared. Prove that. But what do? You break it up, you use the distributive law, blah, 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 and eventually you will manipulate the symbols so the two expressions are linked, right? They're linked by proof steps. We'll do the same thing here, okay? This is called algebra. What do you think that is called? It's algebra 2, but it's Boolean algebra. Boolean means something is true or false. So Boolean algebra is a special branch of algebra to deal with stuff that can either be true or false. Okay, so we'll go ahead and take a look and see how we can do that. What time is it? Oh. We still have time. Good. All right, so what we'll do is we're going to start with this conclusion, which is what we know for sure is true at the end of the execution of that code. And then we'll do something about this, okay? One thing we can do about it is the distributive rule, which is almost the same thing as what you normally do in algebra, except in this case you can distribute conjunction over disjunction. Okay. You are not going to require, you will not be required to do proofs like this. That's kind of the thing for cisp300, but I want to show you that this can be done. That is the most important point, is it can be done. Okay. So you just kind of distribute all the terms. So now we get, let's see here. All right, so you basically just distribute, we end up with 4 terms, and they're all going to be connected by ORs. Okay, so we have 1, 2, 3, 4. Okay. Let's see, are they all going to be connected by ORs or ANDs? No, I take it back. They're all going to be connected by ANDs because we're distributing over the ORs. Okay, so these are all ANDs. And then within each term, they are separated by ORs. So there will be one thing or another thing. Same thing over here. Okay, let me just copy and paste. Copy, paste, paste, paste. And what we'll do now is we'll take this one, we'll put it here, and we'll put it here, and then we take the other one, which is here, we'll put it here, and we'll put it here. And then we go to the other side, we pick up this guy, we put it here, and then we put it here, and then we pick up this guy, and we put it here, and the last spot, which is all the way over here. Okay, I know this looks really messy, but we want to see whether it makes sense or not, because we are basically doing a quote-unquote cross product. So every combination of combining one of these two with one of these two should be in the final list here. So the first term, which is this one here, takes care of combining this guy and this guy. You look at this term here, it takes care of combining this guy with this guy. This term takes care of the second item out of the first pair with the first term out of the second pair. And then the last one takes care of the second term of both of them. Is that okay? This part is mechanical. It is completely mechanical. Basically, we are saying that, okay, I'll just give you the whole thing. Okay, first of all, this is what we know in Boolean algebra. It's an axiom, okay? You don't ask why we get that, well, you can actually prove it too. Okay, let me just show you what I mean by that. Okay, actually, it's the other way around. And so A and B or C. Okay, we start off with an expression like that, which looks kind of like what we have, but not exactly. But this is the basis. This is the basic rule that we have. And my claim is to say, hey, if you give me something like this, I can rewrite this to become A or C, the whole thing, and B or C, the whole thing. This is my claim. Okay, this symbol means equivalent to. Okay, which means the left-hand side and the right-hand side are interchangeable. But how do we know that is true? In normal algebra, you just take it as an axiom and just say, yeah, well, that's true. But in Boolean algebra, you can prove it. How do you prove something like that? You say, okay, A, B, and C are independent Boolean variables. What that means is when A is true, it doesn't imply B or C has to be true or false. None of these three variables depend on each other at all. So now the question is, I know each one can only be true or false. How many combinations of true and false can I end up with when I have three Boolean variables? What do you think? When A is true, B can be true or false. When A is true, B is true, C can be true or false. So how many of those true-false combinations do I end up with? Think about that. A can be true, A can be false. But when A is true, B can be true, C can also be true. Is that okay? When A is true and when A is true or false, B can be false. But all this time, C can remain true. Is that okay? Oops. I think I just need 4 more. 1, 2, 3, 4. There we go. T, T, F, F. What do I put here? False, 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 false. How many rows do we have? 1, 2, 3, 4, 5, 6, 7, 8. How does 8 relate to 2 and 3? We know how it relates to 2. There are many ways 8 can relate to 2. But what about 3? 2 to the power of 3. Okay? So when you have 3 independent variables, and each one can only have 2 possible values, the total number of ways to combine the true and false is 2 to the power of 8. Okay? Okay, why is this important? Well, now that I know the first row has A, B, C all being true, now I evaluate this expression. What do you think this whole expression is going to be when A, B, C are all true? The whole thing is true. Okay. What about the second expression? What happens to this expression here? What is the value of this expression when A, B, and C are all true as well? Okay. So instead of working on the entire table, which is going to be absolutely boring, I'll just pick some random row to do. Okay, we'll just pick this row here. Okay. And by the way, this is a false. Okay. All right. So this says, A is false, B is true, C is false. What do I end up with this expression? A is false. Oh, if A is false, the conjunction of false and anything is going to be false. So we have false on the left-hand side of the OR. C is also false, right? What is false or false? It's false. Okay, very good. What about this guy? A is false, C is false. It is false. But if this side is false, the whole thing has to be false. Okay. Do you think this is coincidental? That we have true and true here, we have false and false here. It is not coincidental. If you work out every single row, you will find that whenever this expression is true, so is this. Whenever this expression is false, so is that one. Then you have an exhaustive proof that for every possible combination of A, B, and C, this expression is always the same as the other expression. That is a really cool way to prove in Boolean algebra why those rules work. Are we doing okay so far with the rationale? I mean, the detail is kind of, it takes a lot of work. Is that okay? Yep.
Actually, I just have a random question.
Yeah, go ahead.
Say you had true or false, would it go straight to false?
If you have true or false, by the time you say true or, I already know the whole thing is true.
Okay.
Because if you look at the truth table of disjunction, it says that if at least one side is true, the whole thing is true. So by the time you say true or, I don't need to know the rest. Does that make sense?
Yeah.
Yeah.
I was thinking if it went straight to false, then the only possible way it could be true is if all three are true.
Okay, so, but this basically establishes that this expression can be rewritten as this expression because they are truly exactly the same. So I'm just applying that, twice, with the stuff that we have talked about. Is that okay? So I'm gonna leave the mechanical aspect, just alone because, that's not the point. What is the point then? Okay, so what we want to do now is to say, we look at this mess here. Can we do something about this? Can we simplify this? Okay, what is it saying? It's saying x is greater than y or x is less than or equal to y. I don't even know what x is or what y is. But what do you notice about these two expressions? X is greater than y as opposed to what x is less than or equal to y. They are negations of each other, which means one of them has to be true. Does that make sense? Give me any two values. Give me any two integer values. Okay? One of these two has to be true. Is that okay? Wait, if one of them has to be true and they are connected by a or, what is the conclusion? The whole thing has to be true. Whoa. I like simplifications like that because it means this entire thing, okay, going from here all the way to here, is just saying true because it has to be true all the time, regardless of what is x and what is y. Are we okay with that? Okay. Okay, that I have simplified. Let's take a look at the second one. We look at this guy here. There's not much we can do about this because the two expressions involve different variables. So I can't really do much about this. We just have to copy and paste it. Nothing wrong with that. And we can get rid of some extra parentheses. So I just get rid of the extra parentheses that I don't need anymore. Okay. What about this guy here? Can I do something about this? Nah, not much. Okay. So we'll just go ahead and copy and paste it. Okay. Copy and paste. Okay. And get rid of some extra parentheses that I don't need. There we go. And then we have the last one, which is this one here. Can we do something about this one?
Yes.
Now, what? No, can't do much about this
I'm
one.
gonna defer to your expertise.
Sorry?
If you say no, I agree.
Well, we can't really do much about this because there's no way to simplify it. Okay. So now we have this one here. I want to do something about this. Can we do some simplification and get rid of the true? What is true and whatever? Is whatever. It's just like 1 times whatever is whatever. Because true is the identity of conjunction. Okay. How do we know that? How do we know that true and whatever is just whatever? How do we know that? How do we prove that is the case? Just because I claim that doesn't mean it's true. We use the same mechanism. We use a truth table. Okay? So we use a truth table. So this time I only have one variable, which is x. X can only be true or false. What is the expression? The expression is true and x. When x is true, what is true and true? True. When x is false, what is true and false? False. True, true, false, false. I have just proven that x is really the same thing as true and x. Which also means the opposite way works too. If you see true and whatever, just say whatever. Is that okay? So all of this stuff can be proven. All right, so that means, in this case, I can simplify my equation by getting rid of true and. Okay, so now we have something that's kind of like what we want, but doesn't seem like exactly what we want. Okay. But are there any questions at this point? Any questions before we move on? Questions? Now we take a look at this expression here. Is there a way for me to relate z directly to x? How do we do that? How can we relate x to z directly without going through y? Well, if z and y are exactly the same, and okay, that's an or. I might have, did I mess up? Okay, just hold on 1 second, let me think about this a little bit. Distributing over the or. We know this piece is what we want. Okay, so we look at this piece here, and then we say, can we change this to a different way of expressing it? Distributing. Yep, there is a way to rewrite this. Okay, so what we do is we distribute the disjunction over the conjunction, which is the opposite of this thing here. Instead, we have an or in the inside and the and on the outside. But it's still true that you can actually just do the distribution. So when we apply that distribution, let me see, do we have enough time? Yeah, we got only 2 minutes left. So I'm going to finish this proof, and on next Wednesday, I'll show you guys the complete proof. Okay. We won't be meeting on Monday. Remember, Monday is a holiday here, and I think some people mentioned that it is not a holiday elsewhere, and that's why some people may not know that Monday is a holiday. So we're not going to meet on Monday. We'll meet on Wednesday, and your homework assignment is due on Wednesday. So have a nice long weekend. Remember, Monday is off.